Alexander Gordeev. I will moderate and manage this session. Let me start our session. I would like to, requirement of our session is 15 minutes for the report and 5 minutes for the questions. I would like to invite our first speakers, Oleg Chaplina, Oleg Chapla, Halina Klim.
Yes, good morning. May I start?
Yes, Oleg, you can share your presentation. Go ahead.
Okay, do you see my screen?
Yes.
Good morning, everyone. My name is Oleg Chapla. I'm a PhD student in Lviv Polytechnic University, and today I will be presenting our work with Helena that was created with Helena Klim. It's named Extracting REST API Endpoints from Microservices using LLM Agents. At first, I would like to say that this work is more practically oriented, but also adds some novelty in the scope of approaches and techniques how do we work with the source code. Our primary research goals were at first improve the process of creating API documentation. In the current scope, we are thinking about microservice as a black box that we don't know anything about it as a developers, but software system may know something. A second goal was to automate the process of API creation, reduce the documentation creation time and maintenance time. Why we set up these goals? Because we have several challenges in managing API documentation, especially for big systems. And these challenges are, at first, when we are building cloud computing systems, in the modern world, we at least divide services into smaller services, they are called microservices, and each service may contain some specific APIs in the scope of some domain. When we have a large system, we don't have one or two services. We may have 10, 20, or even 50 or more services. Therefore, we need to maintain documentation for each service. Each service is maintained by a team or by a person. And we need some time to maintain the documentation, because when a person is developing service, this person needs to look up through the code, validate APIs, prepare documentation, write it, or use some API documentation tools, techniques, or frameworks which propose the ability to create it from some metadata, for example, or tags. Also, inconsistency in documentation may reduce integration time, complicate some integration by introducing some errors and increasing the efforts between the development of such system. Therefore, here are two examples of very large-scale systems from Amazon and Netflix. As we can see, there are too much services, and this means that for each service, some kind of documentation maybe should be prepared. There are several ways how to do it right now. At first, a manual service, API documentation creation, management, and maintenance. This is like very raw approach without any tooling. It's hard. It's very applicable to very small prototypes or medium or up to medium-sized systems. Then we can use existing programming language tools and frameworks. These tools are framework dependent, and when we have a distributed systems with various kinds of services written in different languages like Java, C++, Go, Rust, therefore, for each of such systems, we need to select a specific framework which provides this tooling. Second, maybe drawback, is that these tools require to add additional metadata in the code, like GS-doc, for example, and this metadata should be controlled by the user. So there is no way to automate the full process. For some kinds, there is a way for automating, but the details are not completed because we have two parts in the documentation. The first part is embedded in the code, like API methods, requests, body, but some parts are dynamic or even human manageable. Therefore, system doesn't know for any descriptions, any summarizations about the APIs, any additional information which might help developers. In the scope of this work, we worked with a Node.js framework and checked various kinds of existing tools. We have GSDoc, OpenAPI generator. We have some works like which use LLM agents, but they require browser to fetch the data, but not from the microservice as a black or white box. Therefore, we prepared several steps for improvements. At first, literature review approaches tools. Second step was to determine like pros, cons, and drawbacks based on the previous analysis. The first step, the third step was to design and develop a proof of concept of system that will improve these drawbacks. Evaluate, test on several repositories. We choose 10 repositories. But as you can see later on the table with the results, some kind of pattern appeared. And after that, extract compare results and prepare conclusions on them. The architecture of a proposed approach was to create a separate application in the current scope. This application works on a local machine, and it consists of from two parts. The first one is a source code repository, which is connected to the app. Then we have specific orchestration. This tool manages overall process. Then we have source code data is a storage that stores JSON files, dependency graphs, metadata information, results from parsing for future use. Also, dependency extractor and source code parser are more like static analyzers because they just take repository, run one time through the code, and after that produce dependency graphs, dependency graph image, transforms graphs into our representations that we need, reduces information, filters information, and also applies the results from the LLM agents. In our scope, LLM agents are large language models with some inference service, and they are working in a scope of our application to extract specific kinds of information and building the overall like API documentation. And of course, descriptions are like API descriptions represent the results of it, and generated OpenAPI YAML file is a final result of it. How the process looks like. So we select repository, create dependency graphs, then filter reduce complete information. For that graph, transform it into another kind of representation. After that, run this graph through LLM agents, and as a final step, prepare results and create a final YAML file. This is a result from a dependency graph for one service, but we can clearly see a pattern. On the left, we can see a JSON like representation. We see source files, dependencies, relations between them, names. Why it is necessary to have two kinds of graphs? Visual representation is for human validation, and for us to understand patterns and specific kinds of like a service architecture, what folders we have and what information consists in these folders. On the left, this is for LLM agents, and this representation just tells in a more software-oriented format for agents what we have, like what source files we have, their dependencies, and so on. It's necessary because LLMs, large language models, when they are inferencing, they have a limited context size. For modern inference services provided from OpenAI or MS Azure or Google, they have context size big, but it's always there might be a case when information will be trimmed. So putting just all source code into the LM, it's not okay from a security concerns, from a context window size concerns, from a costs calculation of tokens, input and output tokens, and overall parsing. Therefore, as a result, we also receive two kinds of information. First one is YAML file with a description, and second, the visual representation of that file. It's necessary to have two kinds because from a human or like an engineer's point of view, we are working with that files. Like any engineer is working with a visual representation because it's easier and because developers and engineers are creating the system at least, and they can easily validate what kind of information we have. They can reference to this graph to fill the gaps, because LLMs provide results not with 100% of precision. They provide like a 90-95 precision. Why? Because the mechanism how LLM works is based on a prediction, and this prediction is mathematically described, and therefore it doesn't know the context like we humans know. LLMs does not know the relations between files in a graph format. They are only oriented on a text, and therefore they can like manage to have to understand some relations between text only when the names of different classes, instances are the same or similar. When they are different, or when dependency injection architecture approach is used on when we have separate files in separate folders, but not connected together or dynamically loaded like plugins, it won't clearly work with the LLM, and that was one of the drawbacks. Regarding gathered results, we tested up to 10 repositories, but presented text because we can see clearly some kind of pattern. At first, we need to know source code files, how many we have them, and also lines of code, because it impacts input and output tokens that LLM produce and also costs. Then, when we are processing each file, there is some network lag to transfer information to inference service, to process it, to generate and receive results. Therefore, for a graph processing time, when we are working on a local machine, it's very small, therefore it might not be taken into account, but we need to take into account three groups, like a minimal processing time, max processing time per file, and summarization. When we have very different kinds of lines of code, there are source code files with lines of code. Therefore, this time will be bigger and bigger. And OpenAPI file creation, this metric represents a summary. So we are taking each file, then processing from the transformation pipeline using several LLM inference steps. And after that, the gathered information, it's cleared, filtered, we have prepared data, redundant information was completely reduced from the scope. Like redundant information, it's like some environments, some libraries, which does not provide valid information for this research. Entities may be reduced. Therefore, this information is put into the latest step, to the latest agent, which should produce the final file, this file. As we can see, there are not 100% validity because of the drawbacks I said before. When the code contains dynamic parts, when the code is loaded dynamically, where there are inconsistencies in namings, the system cannot use all the features like LLMs, and therefore sometimes we have a less amount of endpoints. At least this is better than nothing, because we engineers and developers have very good starting point and foundation to have a file, to have almost all descriptions, and they can just manually do some changes and improve or maintain the document. So it's easier to generate a file up to 1 minute and then fill the gaps than managing it more from scratch. The pros and cons proposed approach, the pros that we have a service, it may be a white box or black box even for a user, and the process is automated. The second pros is that we have just up to 60 seconds of extraction time. Results are valid, OpenIPF is valid, but with the minor inconsistencies, 90-95%. It really reduces human time for maintaining and creating that file, and provides a foundation and ability to further source code analysis because having this foundation, we can build another tools on that. From a cons, I would like to say that security and legal concerns, additional costs when working with LLM models. Source code should be accessible to the user, because sometimes we have a private repositories, and it's with a restricted access. And tools that build dependency graphs needs to be adapted to various kinds of programming languages if we want to scale the system. As a conclusion, we set a goal to optimize the process and improve it. The goal was achieved by implementing the prototype proof of concept, tested on 10 repositories, and as a result, we generated valid files with a 90-95% accuracy, which reduces human creation and maintenance of the documentation time and provides some foundation. Our future steps are scaling the system, deployment the system, working with the many repositories, and connecting repositories together into one system that was represented on this image. So when we have many systems, we can tie them together and prepare some information about all of them, like context. I think, and security and privacy aspects may be improved. I think that's all. Thank you for your attention.
Thank you, Oleg, for your report. Who has a question, please? Please, Daria, go ahead.
Okay, thank you. I have a question. Thank you, Oleg, for your presentation. Do you have maybe some statistic how companies currently use LLMs to manage and document microservice-based API infrastructures?
Yes, I can tell that currently many companies are trying to integrate LLMs in their SDLC process. Regarding the complete numbers, I can think that they are represented in several papers, which I might provide later. From my observation and even from my real experience, many companies currently are trying to integrate the system, but they are lacking enough experience or willing to move towards LLMs regarding the security and privacy concerns, because this security and privacy and legal concerns are the major blockers for them, because each company has its own classified information, private information, or even information that is compliant to various standards like GDPR or HIPAA for medical data and so on. And therefore, we might integrate the system, but it can't it can't use full context.
Okay, thank you.
Mm-hmm.
Thank you for your answer.
Who has any question, please? Okay. no questions. Thank you very much, Oleg, for your presentation.